My name is Nabawanga Afwa, and I'm going to take you through our project, which is called Reinforced Deep Q-Knowledge Distillation for Bovine Respiratory Disease Detection using Multi-Strategy Learning. So to go through the background and introduction, basically the background of this bovine respiratory disease, it basically affects cattle and it specifically affects the respiratory system of the cattle, thus leading to effects such as reduced productivity, increased mortality rates, and then thus increasing their treatment costs. So uh, for the introduction, basically the goal for this project is to go ahead and develop an automatic BRD detection using machine learning. Then for the data, we use sensor inputs. These sensors go ahead and detect like the temperature, then the respiratory rate of the cattle, thus enabling us to determine whether basically this cattle is healthy or affected by this BRD. Then the outcome, they are basically alerts, like it goes ahead and alerts the farmer with maybe with signs like reduced losses, like the moment the farmer maybe sees a sign of a reduced loss in cattle, that basically shows that the cattle is like it's not healthy. So automatically indicating that the cattle is affected by BRD disease. So a brief visual flow is here, whereby we have the sensors which go ahead and sense like the temperature, whether the temperature, okay, depends like the range. If the cattle ranges between this and this temperature, it's healthy. If it doesn't, then it's affected. Then we have the sensors. We go ahead and detect the respiratory rate or the temperature. Then we go ahead and collect the data. Like these sensors go ahead and collect the data. Then they send that data to the machine learning model. Where this machine learning model is the one that basically goes ahead and detects. After detecting, then it sends an alert, like an alert message to the farmer to determine whether the cattle is either affected or healthy. Then we have a literature review. The literature review basically it's an insight, or I call can I call it like it's a comparison of what was there in the recent years and what's basically here currently. So to give a small view of what was there in the recent years, basically their BRD diagnostic methods were subjective and time consuming, which led to treatment delays. But for now, in our literature review, it highlights the growing use of machine learning and then precision livestock farming, thus getting rid of this bovine respiratory disease, which is a major economic loss in the cattle industry. So basically, how has it, like want to see like in this literature review, how this machine learning, like how is that how it has helped to get rid of this bovine respiratory disease? Basically, it's through the machine learning algorithms that can go ahead and analyze this sensor based data. Like the moment the sensor goes ahead to detect the temperature, it brings that data to this, and then the data it's detected. After detecting, we go ahead and get to know, like we get notified or an alert to, and then we get to know that either the cattle is healthy or affected. So the moment we use these algorithms, basically they enable us to get timely interventions, thus improving on animal health. So by integrating machine learning and precision livestock farming, a more holistic approach can be adopted through advanced monitoring technologies, thus optimizing and reducing antibiotic use, which contributes to more sustainable and data-driven livestock management practices. Say something on problem statements. We basically have a domain application problem and a computational application problem. The computational application problem, basically, the computational problem focuses on developing an efficient algorithm that can go ahead and improve the computational complexity. Then for the domain application problem, for it goes ahead to focus on applying machine learning techniques to real-world domains, that's real-world domains that require domain-specific knowledge and expertise. So here in our slides, you can see that the domain application problem basically focuses on creating a practical, just like I said, a real-world domain, like requiring domain specific knowledge and expertise. So it goes ahead to focus on creating a practical, cost effective system for early detection of this BRD disease, thus integrating seamlessly into farm operations. Then for a computational problem, like we said, that it focuses on developing efficient algorithms and improving computational complexity. Thus, like it basically involves developing robust binary classification model. This model which goes ahead to distinguish whether the cattle is healthy or affected using this sensor data that we acquired through the sensors. Then to test something on our research questions and objectives, went ahead to have research questions like how can machine learning models accurately detect early signs of BRD in cattle? Like accurately, like we are talking about accuracy, how are these models going to accurately provide data, like to get to know that yeah, this cutter is affected or not, like the one specify the accuracy. Then what are the most significant features? Talk about when I'm talking about features, I basically look at the temperature, look at the respiratory rate, the feeding patterns, like can I go ahead and use the temperature, like is the temperature feature good enough for me to go ahead and conclude that this cattle is affected or not? Then how can real-time monitoring systems integrate machine learning to improve BRD detection? A system like ours, like what is comparative performance of supervised versus unsupervised learning models in BRD detection? Like we go ahead and make a comparison of supervised and unsupervised learning models, and how can transfer learning or deep learning models improve BRD detection in diverse cattle populations. Went ahead to have objectives. Basically, our first objective is to determine the effectiveness of the machine learning model. Basically, when I talk about effectiveness, we just want to assess how well the model will perform in solving the problem. Like, will it provide us like accurate information, like how well is it going to provide us the information. Then to model a real-time monitoring system, here like we mean like create a system that provides continuous data, like a real-time monitoring system. We want data to be provided continuously. Then to evaluate the performance of the developed system, evaluation is basically concerning the accuracy and the efficiency, like how the system is going to be performing in terms of efficiency and accuracy. Then to assess the generalizability of the machine learning model. So basically here we want to assess is the model, like will the model work well on new or unseen data? Like if we go ahead and provide the model with new data, will it continue working well? So some of the research questions we have, like these research questions, we develop them from our objectives, whereby we develop a machine learning model capable of accurately classifying cattle health or BRD affected. Then we built the first real-time monitoring system that goes ahead and integrates machine learning algorithms for early detection of BRD disease. Then we evaluated the performance of the developed system against existing methods, thus improving accuracy and sensitivity. Then we assessed the generalizability of the machine learning model by testing it on diverse datasets, that's ensuring its applicability across different cattle breeds. Thank you.
Hello, my name is Dumba John, and from where my colleague stopped from, I'll continue from the methodology. And here we have the data collection, the data processing, feature selection, and also the machine learning, like training and evaluation. So, starting from the data collection or the data acquisition. So here, we collect the data, mostly according to our project. We are dealing with bovine respiratory disease. We want to detect it uh, during the early stages. So according to how the cattle, like its movements, the temperature, like the sensory data, sensory data that you get through the sensors, like uh, temperature, activity, respiratory rate, feeding behaviors, movements, and many other essential details. So after collecting that data that describes how data was collected from the sensor, including like the frequency of readings, data methods, and any like pre-processing steps applied to the raw data. So we go to the next step, which is data processing. And here there is a splitting of data, a labeling, also cleaning, depending on how our data is organized. So when we clean our data, like we want to address are there missing values, are there outliers, or is there any noise in the sensor data? So we try out to clean the data before we get any problems in the model. And also alongside they have like the feature engineering, creating like the relevant features from the raw sensor data. For example, if we have like the rolling averages of the temperature or the respiratory rate. So in the data processing, as I mentioned, we have labeling where we are like we explain how the uh, like how the cattle were labeled as maybe healthy or like affected by the disease, BRD disease. Then finally, by splitting the data into like dividing the data set into like training and also the testing sets. And in most cases, we take like 70 to 80% to be part of the training and maybe validation or like evaluation. Then the testing set is the least one, like maybe like 20% of that data set. And when you go to the feature selection, we want to know which features should we use and which one, which is the target that we should base on. And finally, we have the machine learning, and here we want to develop a model and train it according to how we want it to evaluate the data and give us the good exact output. And here according to how we have selected our model, want to justify like the choice of the learning model. Are we using reinforcement, deep Q knowledge, distillation, or any other? So according to our methodology, for us, we chose the reinforcement learning. So among the model evaluation, we got the validation, the testing. Uh, Going next to the EDA visualizations. And when we ran our explanatory data analysis visualizations, we got to get different analyses. So below are some of the graphs that gave us how our data is distributed. And so in the machine learning process, after evaluating the model that we did, we got a learning rate of 0.0001, but the training rate was about 10,000, and the accuracy plus accuracy and also the precision, both the accuracy and the precision, we got 92.17%. And finally, when we developed a machine learning model, it was able to accurately detect the BRD disease using the sensor data. We also built a real-time monitoring model for this early BRD alerts. So, and we also achieved high accuracy, sensitivity, and specificity, outperforming existing model. And lastly, demonstrated model generalizability across diverse cattle population. So, this model can easily simplify how we detect this disease, because it's a very disturbing disease whereby if the farmer is unable to analyze or get to know the symptoms early enough, the disease develops and it gets detected at a later stage. So with this model, we can be able to detect it early. And some of the limitations that we face we have limited data set diversity, whereby uh, the collaborate whereby we suggested that we will collaborate with multiple firms to collect more diverse like data so that we can compact in more data for the model to learn. And then sensor accuracy issues, whereby we also suggested to use high quality or like calibrated sensors and regular maintenance. All these, when they are used in the model, they make it accurate and give it it is able to learn faster and well to give us a dependent result. So dependency on the connectivity, whereby to solve it, we could implement offline data storage and periodic syncing. And also lastly, the model generalizability. And here, by testing and tuning the model on additional cattle breeding and environments. So among the future works, want to integrate an IoT device that will enhance the real-time monitoring with advanced IoT sensors, explore deep learning, also develop mobile apps and many others. So among the recommendations, we want to collaborate with the veterinary experts for data validity and also get to know more that we, in case we have missed anything. Also want to focus on the cost-effective solutions for wider adoption. And lastly, they conduct field trials to test system reliability in real world conditions. Therefore, we extend our gratitude to the institute and also authorities for facilitating resources, also the team members and the collaborators for their assistance. And below are some of the referees that you can also look at. Thank you.